see here. So Alice sends a light signal over to Alice prime, who then reflects it back like that. And let's suppose that Alice receives that this is CG. And that's CG A prime. And this is measured meters. Okay. So let's suppose that this is also 45 degrees filters. Okay. So this is the situation here. So Alice just sends this light signal, it goes to Alice prime, and it comes back, and the total round trip time is 12 on her clock. Can she tell how far away Alice prime is with that information? How far away is Alice prime? How far away is Alice prime? 6. So we know the distance is 6. That's because these are 45 degree triangles. So that's 6. This is 6. And this is 6. 6 and 6 is 12. Okay, so basically it takes 12 units of time to go there and back. And so 6 units of time to go there. And so it's basically 6 units of distance. Okay? That's what radar range is. Okay, that's how you determine distances from objects. Okay, like radar range, they determine where an airplane is. You send out a radio wave, the radio wave goes out, hits the airplane, reflects back. You find how long it takes to get there and back. Okay, so we need to get out of the meter stick, like 1 meter stick next to that one. Okay, so let's go. Can you see how we might be able to use this situation to synchronize the clocks as well as measuring distance? So I'll let you think about this. This is, I just want to write down the word radar ranging. Okay, and that's how you measure distances also, well, much more distant objects. Okay, so how do we use this for clock synchronization? This event over here, when Alice's clock reads 6, what is Alice's minus clock read? 6. You should also read 6. Okay, so from Alice and Alice prime, who are about perfectly respect to each other, they can claim that these two events are simultaneous. If they had, say, a light source in the middle, which sent a light signal to both of them like that, they would find those two events are simultaneous. Okay, so the way that Alice and Alice prime can use this procedure here to synchronize their clocks is Alice just sends a light signal out. It takes Alice prime, she reflects it back. She takes the total time, so the total time is 12. She divides that total time by 2, and she says, this is 6. So, and then after the experiment is over, after she receives the light signal, she yells out to Alice prime and says, hey, when you got that light signal, your clock should have read 6. Okay? And then so Alice prime says, oh, my clock read, maybe 10 when I received that signal. So what I do is I move my clock back 4 units. Okay? And then forevermore those clocks are synchronized. Okay? Does that make sense? Are we clear about that? Okay. So one of the things about this is this is a physical process. Okay? Anything that we do in nature, anything that we're always subject to the laws of nature. And so this process of synchronizing the clock is a physical process that uses a physical phenomenon of light. And we know something about that physical phenomenon. According to principle T2, whatever light is, it moves at a speed that's independent of the motion of the source. And in this case, both sources, both Alice and Alice prime, which are reflected, are at rest. And so sort of trivial thing, but we do know that. Also, it applies, this is an important point, this physical process, according to the principles of special relativity, principles T1 and T2, applies equally well to moving observers. A pair of observers who are moving with respect to Alice and Alice prime. Okay, so suppose we had, say, Bob and Bob prime on two ends of a platform like this, and this platform is moving with some speed b relative to Alice and Alice prime. They can use exactly the same process. Send the light signal, Bob sends the light signal to Bob prime, it comes back, Bob divides that time by 2, the total of that time by 2, and then yells out to Bob prime, that any pair of inertial observers, say this pair compared to this pair, moving at uniform relative velocity, are equally entitled to consider themselves to get rest. Okay, and then by principle T2, we know that if you're at rest, the C to C independent of motion source. Okay, yeah.
Actually, the T and the light, the light for multiple times, these are only two, and when the time through there, the multiple times to go. So what's moving towards both the light both times.
That's exactly right. Okay, so let's look at that. So all of this gets interesting now when we look at the Bob and Bob prime clock synchronization experiment or process from the Alice and Alice prime point of view. Okay, so let's do that. Okay, so and I want you to be convinced that this is valid for Bob and Bob Prime to do that. So according to the principles of relativity, so we're trying to understand the nature of the universe based on these principles. And if the things that we predict based on those principles turn out to be true, then we gain some confidence that those principles might actually be a fact of the universe. If they turn out to be wrong, well, then the principles are wrong. So it's very important to understand that these principles are not laws of nature. I mean, they're just guesses, right? I mean, they could be wrong. They're subject to experiment. That's very important. So, but what we do in physics is we guess. We guess some certain principles or some certain equations, and then we try it out, and then we see how far we can get with those. And as I just say, so far, these principles are the most accurately, one of the most accurately measured principles in all of physics. They measure with extreme precision. And so here's our situation then. So we've got Alice Prime, and they're doing clock synchronization procedures and rearranging, determining the distance, all that kind of stuff. That's happening here. And we've also got Bob and Bob Prime, who are moving with some velocity v on their little platform relative to Alice and Alice Prime. Okay, but from their point of view, they're equally entitled to consider themselves to be at rest. Well, let me just sort of sketch something like this. So this little dashed line here is basically Bob and Bob Prime's space, which is moving with that platform. Okay, and the bigger dashed line here is sort of like Alice. They call this AA Prime space. Okay, so this whole space, the blackboard, is the Alice and Alice Prime space for which things are at rest. And here's the Bob and Bob Prime space. And Bob and Bob Prime are moving in the Alice and Alice Prime space. But Bob and Bob Prime, they're equally entitled to consider themselves to be at rest, and they have their own space, which is the Bob and Bob Prime space. And so Bob and Bob Prime and their space, which is moving with them, is moving through the Alice and Alice Prime space. Okay. Now, in the Bob and Bob Prime space, if we were inside that space with Bob and Bob Prime, those guys are equally entitled to consider themselves to be at rest. All they're doing is they're standing at two-dimensional platforms, and they apply this clock synchronization routine. And from their point of view, what does it look like? It looks like this. Here's Bob Prime. Bob sends a light signal over to Bob Prime. Bob Prime reflects it back. So Bob sends a light signal over to Bob Prime. It gets reflected back. Bob looks at the amount of time, the total amount of time elapsed. And what does he do? Divide by 2. He takes that total time, whatever this is, 1, 2, 3, 4, 5, 6, 7. Divide that by 2, 1, 2, 3.5. And he concludes that this event is simultaneous with that event. Okay, so simultaneous in the sense of this. Okay, these two events are simultaneously happening. For me, they're happening at the same instant of time. Okay, so when I click them like this, sure, there's I'm at rest with respect to the air, and it takes time for those sound waves to get to my ears, so I can hear, but it's obviously equal time. Okay, I can hear them at the same time, and they're happening simultaneously. Okay, so these two events are then simultaneous. We'll call them, say, P and P prime. These two events are simultaneous for Bob and Bob Prime. Okay, so that's important. They're simultaneous. Okay, so now the interesting question is, so this is all sort of obvious. The interesting question is, what does this experiment look like? What does this procedure look like from the Alice and Alice Prime point of view? Okay, Alice and Alice Prime see Bob and Bob Prime moving through their space. But they can still, and they see their light beams and all that stuff, so they can observe that experiment happening, or that procedure happening. Okay, so let's draw that. Okay, so there's Alice and Alice Prime. We're taking the point of view now that Alice and Alice Prime are at rest, so their world lines are vertical. They see Bob and Bob Prime drifting to the right across their frame. So their world lines, okay, take this point over here, Bob crosses Alice's world line, and say, at this point, Bob Prime crosses Alice Prime's world line. With some velocity v. And they do this rearranging experiment, or this clock synchronization experiment. Okay, so what does it look like? Well, let's see. So this event over here, down here is Bob. Bob has emitted a light signal which travels over to Bob Prime. So at this point over here, Bob emits a light signal traveling towards Bob Prime. So the question is, what does that light signal look like from Alice and Alice Prime's point of view? How would I draw that light signal? Yeah. 45 degrees? Wow. That's right. Okay, so it's right at 45 degrees. Let me try to draw this reasonably here. Okay, so this is 45 degrees. Principle P2. Principle P2 says that the source of all of these Bob is moving to the right and left. Bob is moving to the right, and Bob Prime is moving to the right. So, you leave that to the right. So actually, that's right. So Bob and Bob Prime actually start over here, but they're drifting to the right. And so at some point, Bob is coincident with Alice, and Bob Prime is coincident with Alice Prime, which is what's happening here. Yeah. Okay, so at that instant, as they're crossing, as one platform is lined up to the other platform, Bob and Bob Prime start doing this synchronization procedure. Bob sends a signal over to Bob Prime, and that light signal travels at 45 degrees, even though he is a source that is in motion. Right, so Bob is carrying a flashlight. From Alice's point of view, there's a moving source. Bob clicks on that flashlight, but even though the source is in motion, Alice is going to see that light move at the speed of light, which is 45 45 degrees, inverted diagram. Okay? And then what happens? Then that light signal hits Bob prime and gets reflected back. Okay, so at this point here, Bob reflected back. So I'm going to draw a light signal going back, and what angle do I run? See, yes, absolutely. So if Bob is say a red light, and well, it depends. So if Bob, suppose that Bob is just a little bit to the left of Alice, then she will see the light signal passing this way, and so the light signal, you see the approaching, so the source is approaching, and so she will see the frequency blue shifted. If Bob were just to the right of Alice when he sent it, well, then the light goes that way, she doesn't see the light here. Okay, so this guy here is at 45 degrees as well. Again, Fokker motion 2. Remember, we're trying to do everything according to the principles. Okay, thanks. Okay, so we got this guy 45 as well, even though Bob prime is in motion, doesn't matter. Okay, so this is also 45, but now what? The tick marks on Bob's road line here, measuring the time according to Bob. How can I draw these? Are these evenly spaced or not? They're evenly spaced. There may be time dilation. In fact, there will be. So the tick marks in Alice's road line are close together. The tick marks on Bob's road line are further apart because there's this time dilation. But that's not relevant here. What's relevant is that the spacing is even, whatever it is. Okay, so now what happens? What does Bob do? What's the next step in his clock synchronization procedure? That's right. So he counts the total time divided by 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11. Okay, let's suppose there's 10. 10 divided by 2 is 5. So he's got 10 there. He divides that by 2 and he gets 5. So where's the midpoint of this? The midpoint of this is about there. Okay, so that's 5. Okay, so what he concludes is that that's this one here, the event T. And so what he concludes is that this event here, halfway in between, is simultaneous with this event. So that's where Bob prime received that light signal. And he concludes, so Bob prime would say that these two events are simultaneous. So for them, if we were to catch up with them and stand in their reference frame at rest respect to Bob prime, hear them at the same time if they were like snapping finger events. Okay? So, but are they simultaneous for Alice and Alice prime? So which one occurs first? So here's time according to Alice. Here's 1 second, here's 2 seconds, here's 3 seconds, here's 4 seconds, here's 5 seconds. T occurs first, then there's 6 seconds, and 7 seconds. Oh, T prime occurs. So T occurs at 5 seconds, T prime occurs at 7 seconds. Okay, so for Bob and Bob prime, those two events are like this. For Alice and Alice prime, who see Bob and Bob prime doing things like this, they see this event, then this event. Okay, so that's really, really important. That this idea of simultaneity, when two things are simultaneous, that depends upon the observer. For me, these are simultaneous. If you're moving relative to you will see one first, then the other. Yeah.
The light principle is that independent of the motion of the source speed, in their diagram, the other signal going up 45 degrees stop line. And then the Alice's road line is very close to the angle, and Alice's road line stops the road line because of the other different because of the velocity. Yeah, so there's no velocity here. Exactly. So then, when she, like, by that diagram, it doesn't make it she's proceeding like yes. Right? Well, she is, because it's not diagram. That's it. So this is vertical. This is supposed to be at 45. This one's 45. So I mean, when I say 45, it goes to the black one, it goes to the vertical and horizontal to the black one. Okay, so that's that. Okay, so actually this idea that simultaneity might not be relative, may not be absolute, but might be relative, or depend upon the observer, was first suggested by Poincaré, and then a little while later, it was Einstein who actually understood concretely what this means. Okay, so what this means is quite radical. Okay, it's quite beautiful, the consequences of this. All right, so let's look at this just quickly, and then we'll take a break. Okay, so let's talk a little bit about Bob's x-axis. Okay, so we know all about Bob's time axis, right? So in these pictures that we're drawing, that's Bob's time axis, that's Bob's time axis. This is the time, according to Bob, the tick marks along those axes, right? So this is C through Bob, C through Bob, prime, and so on and so forth. Okay, so we know all about time axis. But what is his face axis? Here's Alice's time axis, and here's Alice's face axis. What's Bob's face axis? How do I draw Bob's face axis? Yeah. I see it's up there. Which direction is it tilt? Like that? Like that? Yeah. Oh, yeah. That's this Bob's x-axis. Okay, so let's quickly get this. This is really cool. Okay, so where Bob's x-axis line is not there. Okay, so here is, let's first of all think physically, practically, the platform. The platform, the line between them. Okay, so stretching from Bob to Bob prime,
is a platform. They're both depending on the platform. So, and they're both synchronized according to our synchronization secret there. So when boss clock reads 0, boss clock reads 0. When boss clock reads 1, etc. So it looks like this. This is time according to boss time in their frame. Okay? At t equals 0, how would I draw their platform? The line between them. Just a straight horizontal line. Okay, so this is their platform. At t equals 0. Okay, because the platform, I mean, it's just like this, you know, here's the clock on one end, here's the clock on the other end. When those clocks reach 0 at the same time, stretching between them, when all points of space between them is points of matter, all the atoms taking out that platform. Okay, so what about t equals 1 second, where it's all time? That's just looks like that. And similarly here. So this is a snapshot of their platform at various times. Right. So now let's look at what those platforms look like in this picture here. Look at those, so the picture of those platforms at various times involve a lot of time frame. This is simple. What do those platforms look like? What do those snapshots of the platforms look like? According to Alice and Alice Prime, we see log and log prime drifting to the right. So that platform is drifting to the right in Alice and Alice Prime space. How many are these platforms? So which way? Up to the right one. You got to be between T and T prime. Okay, so according to log prime, that event is simultaneous. So those events for log prime are like this. The platform between log prime at that time expresses just from that event to that event. Right? All the little atoms in that platform, the physical atoms occupy this space here from there to there. Okay, so it's tilted up like that. Okay, so that's a snapshot of the platform at that point. So here's our point T, and here's our point T prime here, and the platform stretches from there to there. Okay, and so different times. Here's an earlier time. Here's a later time. So that's their platform. So notice that their platform has this tilt. We take the angle of this tilt. Suppose that this angle is 10 degrees. Okay, here's a good guess, right? 10 degrees. Okay, so however much Bob's time axis goes, Bob's space axis, or his platform, goes the same amount. Okay, the point here is this is Bob's x-axis. This is the x-axis where he's Bob. This is the time axis where he's Bob. Okay, so the picture that emerges here is like this. So here's space and time, according to Alice. And here is Bob's world line. Here's Bob's time axis. Okay, it's tilted by some amount. And Bob's space axis is tilted by another amount, but not relative to Alice's space axis. Okay, so these angles are the same. So that's not okay, so this is Bob's x-axis. Like that. Okay, so this is very similar to what you're familiar with in Euclidean geometry. Okay, so in Euclidean geometry, we have this sort of thing. So suppose that we have a two-dimensional space here, which is the Blackboard Euclidean space, my space, and Alice comes along and draws a coordinate system on it like this. It says, here's my coordinate system. And when I look at points in my space, I will say, well, there's a point. The x and the y coordinate of those points, that's the x coordinate, that's the y coordinate. And to get the distance between here and here, what would I do? What would I always do? Actually, this is this, what would you do? Would you take this square, root, and give her that? Okay, but now suppose that Bob comes along and says, well, I would like to go back to, so I will draw different axes. So I will choose my wrong axis. So the y-axis, where's the Bob in this one? Where's his x-axis? Okay, wherever that angle is, that's 10 degrees. We tilt it down, it's 10 down. So the x-axis, where's the Bob? It's saying 10 degrees. So what are the x and y coordinates of that point? Well, we draw perpendiculars. We draw perpendiculars to the y-axis and the y-axis. And so that distance is the square of this, square of that distance. Okay, so that's Euclidean geometry. What we see here in Newtonian geometry is if Bob's time over space and time, Bob's time axis is tilted by some angle like this. Instead of Bob's x-axis being tilted by the same angle but down, it's tilted up. And the difference between down and up comes from that slightly larger side. Okay, the geometry is different. And we can also talk about distances here. Alice measures a distance in her space-time between, say, that event and that event. What she does is she draws a triangle like this, and I figure the square of that distance equals that square minus that square. Square root gives me that distance. And Bob prime can do the same thing. Okay? So it's exactly the same sort of thing. Okay, so from here. So, I just want to recap a little bit what we were talking about last time. So, let's think first in terms of space. So if we have, so here is a two-dimensional space. The blackboard is a two-dimensional space. And Alice comes along and she chooses a coordinate system to describe points in that space. So this is her x-axis and this is her y-axis. And if there's some point in this space, she will say, oh, you know what, the x-coordinate of that point is this, and the y coordinate of that point is this. And given those x and y coordinates of that point, how would she figure out the distance from there to there, the length of that line? Pythagoras. She would take this square plus this square to square root gives me that, right? Okay, now Bob comes along and says, Alice, I don't like your choice of axes. I would rather choose these axes here. So this is Bob's y-axis, and whatever tilt he puts in here, 20 degrees or whatever, his x-axis must be tilted the same amount, 20 degrees here, or whatever it is. And so that's the x-axis according to Bob. Okay, now Bob looks at this same point in space here and says, the coordinates, my x and y coordinates for that point differ from yours, Alice. My x coordinate is this one. I drop a perpendicular down like that. And that's my x coordinate. And I drop a perpendicular this way. And this is my y coordinate.